Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking about electromagnetic wave parameters. We've already, at this point, discussed electromagnetic waves a little bit. We've discussed Maxwell's equations, how they predict electromagnetic waves. We've talked a little bit about how accelerating a charge can change the electric fields and thereby produce an electromagnetic wave. And so today, maybe a little bit about the parameters that you get from the equation for the E field and for the B field of an electromagnetic wave. So you will, as always, recall from our previous discussion that we had set up a pair of equations that said that the electric field is given by some maximum field or E naught value times, let's say, the sine of some wave vector times x minus or plus omega times t, and that the magnetic field was likewise given by some maximum magnetic field strength times the sine of your wave number times x, again minus or plus omega t. And these could be vector terms. We generally limit ourselves to 1D waves here, although you could have like a single point source that emits light in all directions, for example. In which case this kwx becomes also a dot product. What we're basically doing today is just breaking down what each of these parameters are and how they relate to each other. And then in a future class, we'll be adding a little bit more detail to them. So basically, this first equation describes the E field. The second equation describes the B field of our electromagnetic wave. And the other thing to note is that certain of these terms have kind of like a fixed relationship. So kW is the same for both. So this right here, kW, same for both. Omega t, same for both. Whether you've chosen plus or minus, same for both. Okay, so all three of these pairs, same for both waves. And what that basically means is that E and B are in phase. You can in fact add an additional plus phi naught term, and that's also the same for both. That's your phase offset. So they're in phase. And it's worth noting that kW is what's called wave number. And as we discussed in mechanical waves, this wave number is actually given by the wavelength, or 2 pi divided by the wavelength. So 2 pi divided by lambda, lambda being wavelength. So that's kind of like the spatial extent of a wave in some sense. So like spatial extent of one cycle of wave. And then the flip side to that is that omega, which is the angular frequency, is related to the period by omega equals 2 pi divided by period t. So t represents period, and that would be, instead of spatial extent, the period would be duration or time extent. of one cycle of the wave. Okay, so you have all that information just looking inside this set of this pair of equations. Okay, so the other thing that you're getting is the amplitude. So E naught and B naught are not equal to each other, but they are amplitudes. That would be the maximum value for each of these two fields. So they are the amplitudes of E and B field, respectively. And you'll recall that amplitude means maximum value. So if you were to sketch out like a snapshot somehow of the wave where this is position and this is, let's say, E, then you would expect to get a wave, that looks sinusoidal like this. And this value right here, whoops, at the peak, this would be E naught. So I guess in blue we're drawing E. This right here should be negative E naught. And this right here, we've completed one whole cycle. This would be the period T. I'm actually going to label that part in black, however. So this is the period T. And if we were to add to this graph, let's say in green, the magnetic field, it basically would look the same as the electric field as far as being a sine wave, as far as having the same period. The amplitude obviously ends up being different because we're measuring a different kind of wave. So this right here would be my B naught value. This right here would be my negative B naught value. Note that they have the same period, however. I mislabeled that though. I said period. This would be if this was in time. So maybe we should do two axis labels here. We could do period and we could do duration. So if we were to look at it in time, the duration equivalent is lambda, the wavelength. It's a little cleaner. Okay. Now, about this relationship between E and B. Well, stated without proof, but you know from dimensional analysis and some earlier discussions that E naught over B naught, these are two constants for this wave, the maximum magnetic field strength, the maximum E field strength. These actually have the ratio of C naught, which is 2.9979248 times 10 to the 8 meters per second. That's the speed of light in vacuum. Okay, so that gives us our maximum values ratio. It turns out that E naught over B naught, if you come back here and look at the way these equations are written, at any position x and time t, E naught over B naught times a constant is going to give me the same ratio. So E of, let's say, x naught t naught divided by B of that same x naught t naught will also equal C naught. Okay, so these are the max values. Then these down here would represent value at any given position in time. So value at a given position x naught at a certain time t naught. Okay. That also means, for what it's worth, that if you took the average of the two and took that ratio, so like E average over B average, we would once again obtain this same ratio, C naught. So these are now the average values. Okay. Now, speaking of average values, this is the other thing where we have to recall something. AC signals, where we had something like an AC circuit connected to a load resistor. For this, we ended up finding a average power, which was essentially the square of the current times resistance. So this was like I average squared times R. And we also had the maximum power, which was the maximum current times R. And from these two things, we were able to find that P average was 1/2 of P max, and therefore that I average was 1/√2 of I max. Okay, so this was all from AC signals. But the AC signal, the very equation that goes with it is that I is equal to some maximum current I naught times the sine or the cosine, as the case may be. We'll use sine of omega t. So in some sense, when you average something that is sinusoidal over time at a given space or over space at a given time, either way, you expect to get 1/√2 of this maximum value as your average value. And so that was the root mean squared value. So I average represented I root mean squared, which was 1/√2 times I. Whereas the power average is 1/2 of maximum power. So that was 1/2 of I naught squared R. Now the reason for all this is that, once again, for both E and B, we have E is equal to E naught sine times kx minus or plus omega t. Could add also a phi naught if we wanted to. B was B naught sine kx minus or plus omega t plus phi naught. And in some sense, if we were to go back to this equation here, this sine omega t term, you could call it sine omega t plus phi naught. I'm going to put a little prime on it, and it could be plus or minus. And the reason why that matters is because my kx, so phi naught prime, could be equivalent to kw times x minus or plus omega t. Minus or plus phi naught. And so this whole thing is just phi naught prime plus or minus omega t. There's, by the way, a w on subscript on both of these k's that I left off from before. So kwx, kwx. Okay, the reason why I'm bringing all that up is because this equation looks very much like this equation from a physics mathematics perspective. So E and B look like I for AC. It follows that we expect the average value of E to look like the RMS value of E, which looks like 1/√2 of E naught. And the average value of B should look like the RMS value of B, which should look like 1/√2 of B naught. Okay? All right, so let's conclude with a quick example. So we have an electromagnetic wave whose E field has an amplitude of 900 kilovolts per meter and a wavelength of 0.25 meters. And what we want to know is the wave number, the angular frequency, and then the average values for the magnitudes of E and B field. So let's start with the wave number. Well, we know that the wave number k wave is given by 2 pi divided by lambda, where lambda is actually right here, the wavelength. So lambda is wavelength. Therefore, the wave number is 2 pi divided by 0.25 meters, or inverse meters, is 0.25 meters, and therefore what we have is 8.0 pi inverse meters. That's a valid answer. If we want an approximate answer, then we would multiply 8 by pi, thus obtaining about 25.13. So with two significant figures, this is about 25 inverse meters. The angular frequency takes a little bit more doing. So you can get it via figuring out what the period is, and we know that c, the speed, or c naught, the speed, should be the wavelength divided by the period, and that omega is 2 pi divided by period. So if you combine these two equations, then you have omega is c naught basically divided by lambda naught times 2 pi. But 2 pi over lambda naught just is the wave number. And so this ends up looking like wave number times c naught. So therefore, omega is equal to, equal to 8 pi times 2.9979248 times 10 to the 8 meters per second. Those of you doing this at home might round this to just 3.00 times 10 to the 8. So if I multiply my previous answer by 3, then it's going to be 75.39 something. So we could call omega approximately 7.5 times 10 to the 9 radians per second, or inverse seconds. That's a valid answer. So there's omega, and these are both the wave number. To get the average electric field magnitude, we use that the RMS value is 1 over square root 2 times the maximum value, where the maximum value is this number right here. So this is E naught. So this just ends up being 900 divided by square root of 2. So 900 divided by square root of 2 gives me 636.39. So assuming that this is 3 significant digits, maybe we would call this 636 kilovolts per meter, or 6.36 times 10 to the 5 volt per meter. To get the average B field, what we would use is that BRMS is E RMS divided by C. So basically divide this number by 3, or 3.00. So if you do that, then you get 212, and then divide by 10 to the minus 8. So you end up getting 2.12 times 10 to the minus 3 Tesla. I guess we could kind of end this by saying, what is the actual E field expressible by? So in that case, E would be 900 kilovolts per meter, assuming that we're using sine initially. The K would be 8.0 pi inverse meters times x. And then if it's traveling to the right, it'd be minus. If it's traveling to the left, it's plus. We'll assume it's traveling to the right. And our omega was basically about 24 pi, 8.0 times 3 times 10 to the 8. So we could say like 24 pi times 10 to the 8 inverse seconds time. So again, this right here is the wave number. This right here is the frequency. This right here means, so traveling to the right. If it was a plus sign, it'd be traveling to the left. And then this right here is my maximum value. So I think that really concludes this example. Video's a little on the long side because I made this example a little longer. But hopefully it's worth it for all of you who've watched it through to the end. And if you are such a person, then thanks for watching all of it. And hopefully you learned something from it. So